worthy of enshrining, but you will get better this week and beyond at tackling these new topics. So a very rapid review of some of the syntax we looked at last week, and then we'll dive into some actual examples. So this was representative of a pair of Boolean expressions and softball question. The double vertical bars just denoted what type of Boolean. So ORing two things together. So either the thing on the left has to be true or the thing on the right. And if so, then you will, quote unquote, do this. This, by contrast, was a Boolean AND, which meant both left and right had to be true. We saw similar constructs in Scratch. And then we introduced conditions as well. So you can have one fork in the road, 2, 3, 4, any number really. But if you kind of extrapolate mentally from some sample code like this, you can imagine perhaps this getting a little unwieldy once you have 5 or 6 or 7 or so forth conditions. So it turns out there's another alternative syntax that functionally achieves exactly the same thing. And this indeed is consistent with this reality in programming that you can do almost anything in multiple ways. This is the so-called switch statement. And we'll see that it's actually a bit more limited than if, else if, because every one of the cases can only, as we'll see, be an int or a char, essentially. You don't want to use other data types, but it simply allows you to enumerate in a slightly more human-friendly way several different cases that you might want to apply. And then lastly, last time, we looked at loops. And we looked at perhaps the most syntactically complex one here, this for loop. And if you looked up during the music a bit ago, you'll see that Foxtrot cartoon, which actually was playing off of this idea of a for loop. A for loop has 3 segments where you can initialize some variables, a condition that you check every iteration, and then one or more updates that happens at the end of each iteration. But we also have while loops, which are a little simpler, but you need some way of breaking out of them potentially. So we'll see examples of those. And then lastly, and this is the one where maybe your curiosity should be piqued just a little bit, that might come in handy in particular with pset1, where you want to do something and then maybe do that same thing again and again and again. For instance, this is a very common snippet of code to use if you want to prompt the user for some input, and they might be difficult. They might type in a negative number. They might type in monkey, as I did last week. And you want to again and again tell them to do something until they've satisfied some conditions. So we'll see this construct in action as well. So without further ado, let me go ahead and pull up the CS50 appliance here. And this is a buggy1.c program. So if you're following along at home or on your laptops, this is included in today's PDF and zip file. But this is indeed a buggy program. It's supposed to print out 10 stars on the screen. But why does it not, in fact, print 10 stars? And what does it actually print? OK, so 11. So the consensus is 11. Why is that? So this is the sort of mistake that should hopefully get easier to spot. We're starting counting at 0, and that's sort of good form, though not strictly required. The problem is, though, that we're counting up to and equal to 10. So if you just start counting on your fingers, that means this loop is going to iterate for I equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's actually my 11th finger, and so that's indeed one too many stars. So an easy fix here might be what? And just make it less than 10. You could just delete this. If you really wanted to, you could do something like this. But again, the former is probably preferred among programmers, just to, by convention, start at 0. All right, so that's buggy1.c. Let me go ahead and open up another one here. This one is supposed to print 10 stars, 1 per line, but it does not. What's the bug here? Yeah? Exactly. So the line break needs to either be inside of the first printf here so that it actually gets applied again and again after every star. Because even though I've indented in this nice pretty way, remember that any time you have a condition like a for statement or a while statement or an if statement, if you have one line of code, you don't need the curly braces. If you have 2 or more, you do. So it doesn't matter how nicely you indent things. You could also fix this problem by including that curly brace there. Another one here for good style. Let me go ahead and move the cursor back where it belongs. And this, too, would work. So again, another example of 2 different ways to do it. Which one might you prefer? The one-liner is kind of nice, to be honest, putting the \n right after the star, because you don't need the curly braces. You don't need a second line of code. You don't need to call printf sort of foolishly twice. And so there's multiple ways, again, to do something like this. All right, how about one more here? So let me go ahead and open up buggy3. And in this case, I'm going to just defer this, because I was not supposed to open buggy 3 at this point in the story. So we'll come back to buggy 3 there. So buggy 3 is going to be pretty damn interesting. So let me go ahead instead and open up something else, just as a sort of warm-up here. And again, raise your hands or look confused as visibly as you can if you have any questions, and we'll pause or slow down at any point. So this is a really stupid program. It computes the total of two numbers mathematically, but that's it. And I point this out because, one, it's actually syntactically correct, but when I try to compile this, I'm not sure GCC is going to like it. So notice the familiar now, include standard io.h. Now, technically, I don't even need that because I'm not using printf here, so this really is a useless program. So I've got int main void, and that's just copy-pasted from last week. Now I'm declaring x as 1, y as 2, and z as x plus y. So that actually looks pretty reasonable. I'm declaring variables on the left and assigning them values on the right. But let me go into this directory, and I'm going to go ahead and type make math1. And unfortunately, GCC is yelling at me. Error, unused variable z, then some crazy looking -w thing, all warnings being treated as errors. Well, what's going on here? Yeah. Yeah, exactly. I may very well have computed z, and it's correct. It is the sum of x and y. But what was the point of this whole exercise? So one of the features of GCC that we've enabled by default in the interest of pushing you toward correct code, as well-designed code as possible, is to yell at you when you do something that's just a waste of time. If you're not actually going to use z, as you might by using something like printf. Printf percent, what would it be for an integer? %d for an integer, maybe \n for good measure. Now this might make the compiler more happy, because now I'm not only declaring z, I'm using z, even though the program itself is still underwhelming. But if I now go back down here, let me zoom in and rerun make math1, now it's indeed happy. And if I go ahead and run math1, I get back the answer 3, which is, of course, 1 plus 2. So just to point out this error message that even when you see things at first glance that look a little cryptic, just read into it, at least the part that, frankly, does not look overwhelming, and see if you can't infer where the error is. In fact, if I go ahead and break this again and delete the printf, let me zoom in and recompile math1, notice that it's actually being a little more helpful than spitting out this message here. Unused variable z, yes, but it's actually telling me, GCC, that it's in math1.c that I screwed up. It's specifically at line 19, and then somewhat less usefully, specifically look at character number 9, give or take. So 9 characters into that row. So it's actually pointing you toward what's probably the error. Now realize this isn't a golden rule. If you actually have multiple errors, you might actually be informed that you've got an error at line 15 when actually it's on line 14 because you've done something wrong above it. So sometimes the compiler can get confused. But again, look for these clues as you try to diagnose these initial bugs. All right, so let me open up math2, which is now trying to do a bit more. So in math2.c, I actually am fixing this problem. So we already did that, so you have a copy of the correct code there. In maths3.c, we're going to go ahead now and use a floating point. But this, too, is actually a little broken. So let's take a look at the code. I've got standard I/O for the sake of printf, int main void, so that's boilerplate. And now I'm doing float answer. So a float, just as a recap, it's how many bits? So it's 32 bits. It's not the biggest possible floating point value, but 32 bits is still a lot. Surely we can represent something as relatively small as 17 divided by 13, which would be 1 point something. You would like to think that 32 bits is enough to represent the number 1, give or take. But then I go ahead and divide 17 by 3 here. I store the result in answer, but I'm then printing it out, .2f. The .2 denotes what? So just 2 decimal places. %f generally means give me a floating point value, but .2 means only show me 2 numbers after the decimal point. What am I plugging in answer? So this actually feels OK, but let me go down here now, and let me zoom in and run make math3. It does compile OK, but when I now run math3, I'm pretty sure 17 divided by 13 is not 1.00. Frankly, I don't quite remember exactly what it is. Pretty sure it's not 1.00. So what's going on here? What's the problem? Yeah?
You're dividing two integers, so you're getting an integer answer that's then being converted to a float.
Yeah, so this is something we haven't talked about explicitly, but indeed when you divide 2 integers in C, what do you get back? Well, you're going to get back an integer by nature of mathematical operations in C. So 17 is an integer. Why? Well, it's obviously an integer, but more specifically, it does not have a decimal point in it. So C views 17 as an int. 13, meanwhile, also looks like an integer. There's no decimal point, so it too is treated as an int. And that's actually a bit of a white lie. It's treated as a long typically, but the results are the same. It is not considered a floating point value. So 17 divided by 3 gives me 1 point something. Well, that something can't fit into an integer. It can't fit into an int, and so the point something something is just thrown away. This is called truncation. So the number is just truncated and you lose that. So even though I'm then taking the answer and I'm saying it is a float, it's too late. You've already thrown away everything after the decimal point when you did the original division. So if the problem then is that answer, even though I'm calling it a float, is actually storing the result of an integer divided by an integer, whose result is an integer, how do I fix this? Yeah, in back. Yeah, so I can actually introduce this other feature of C known as typecasting, or more succinctly, to cast a variable from one data type to another is to cast it. So what you can do is with simple parentheses, you can do something like this. Yes, 13 is actually written as an integer, but I would like the compiler to treat it as though it's a float. And this is actually legitimate because you're not converting apples to oranges. You can reasonably convert an integer to a float. You just add a decimal point, essentially, 0.00000. So now this is effectively 17 divided by 13.0000000, albeit with some imprecision. So now when the division happens, I get back a float. I'm storing that float in a float called answer. And so let's see if my answer is now any better. To make sure to save always with Control S, or the File menu, let me go ahead and recompile Math3. No errors, that's good. And let me go ahead and rerun Math3, enter. Ah, that's the number I was hoping for. So this might be sort of low-level detail, but this is absolutely going to be important. Even in pset 1, where you're, for instance, trying to provide a user with change, and you're dividing some total amount by 25 cents or 10 cents or something like that, you're going to need to beware or be mindful of these kinds of issues that you might literally be throwing pennies away. In fact, if you think now, if you've ever seen the classic Office Space or the precursor Superman 3, you might recall that the scam that they waged in Office Space was to kind of skim the fractions of pennies off of the dollars that were going through Initech, the company. Well, this actually relates, right? Those guys were programmers, and what they were referring to was, one, this inherent imprecision of floating point values that we saw last week, and also the fact that sometimes these remainders are just potentially thrown away. If you've never seen this movie, I do recommend. Yeah? Good question. Why do you have to cast the 13 as a float and not the 17? Well, first, it suffices to only do one of them. So that's fine. And notice what happens here. If I do this and save, then recompile with make math3, and then rerun, so that actually would fix it as well. I just chose one arbitrarily. I could do two. And frankly, there's an even simpler approach. You could certainly just avoid this whole new concept of float, of casting rather, and just say, fine, make it 13.0 and make this 17.0. That might work as well. Yeah? So you can. It looks a little weird, but you could also do this. C is perfectly content with that if you just like the elegance of no trailing zeros. Any other questions on floats? Yeah?
Before you had done the typecasting, so is answer a float or an int?
It's a good question. So before we did the typecasting, is float an answer or an int? It is a float because we explicitly made it a float, but it was assigned an integer value. So what happens there is actually called implicit casting or implicit conversion. So it is indeed a float, and conceptually the point 0 is just appended to it when the equal sign moves the value from right to left. And a question over here? Yeah? No, only one of them needs decimal places. So essentially the sort of more powerful number takes control. So a floating point number with precision with a decimal point sort of supersedes the weakness of an int. And so you just need just one of them. So again, the takeaway here is not that the next time you divide one constant value by another, you should be mindful of this, but rather when you're taking arbitrary user input, maybe dollars and cents, these are the kinds of issues you need to be careful of. And certainly in the real world, if you're the person implementing the next automated teller machine, these are absolutely the kinds of issues you need to be mindful of when dealing with any kind of currency and fractions thereof. All right, so let's transition now to this file here. This is